So today we're going to be talking about noise in MEMS systems. So let's first talk about what noise is in the context of engineering, okay? So in the electrical domain, noise is attributed to the random motion of charge carriers. Let's see, just put found in a conducting material. In the mechanical domain, noise is attributed to the random thermal vibrations of atoms in a mass. So from these two definitions, the most important thing that we can take out of it is that noise is a random process. And what I mean by a random process is that the value of a noise signal, be it an electrical signal or a mechanical signal like a displacement or something like that we're trying to measure, cannot be predicted at any time, even if our past values are known, okay? So as a very simplistic example of a well-defined signal versus a noisy signal, let's consider something like this, okay? So let's say that we have some signal f1 of t that is a simple sine wave, right? So it may behave something like this, where it's starting at 0 and it is going to oscillate between some maximum and minimum value in a periodic way. So because this signal is so well defined, right? So we could say that it has some fixed period of capital T, which is the amount of time it takes for the signal to repeat itself. We should be able to accurately predict a value for f1 of t when t, let me write this down. So because f1 of t is periodic, we should be able to accurately predict a value for f1 of t when lowercase t time is greater than uppercase, sorry, that should be t, not tau, t, the period, because we know how the past values of time are behaving, okay? So this is a signal with effectively no noise. Then down here, let's do f2 of t, once again as some function of time. And we might have something that looks like this. And for what it's worth, you don't need to draw this accurately because it's just going to be a crazy bunch of scribbles. So something like that. So this particular function, so f2 of t, has no period or discernible pattern. So instantaneous values of f2 of t cannot be predicted over any time interval. So if noise is a random process, how are we going to be able to analyze it and or account for it? And the short answer is that while the instantaneous value of a noisy signal isn't able to be known or predicted, the average power of a noise signal very often can be predicted, okay? So if we were to observe how the noise behaves for a long time, we can develop a statistical model for some noises that'll at least give us a range of where we should expect our noisy signals to fall into, okay? So let's talk about the noise voltage for a resistive load. So let's let f1 of t be a periodic voltage signal applied across a resistor R sub L, okay? Our average power in this case is simply going to be the integral of the instantaneous power. Since we're dealing with a periodic voltage signal, I'm going to choose to represent that power as V squared over R. So F1 squared as a function of time divided by RL. So this is our instantaneous power, okay? I'm going to integrate this with respect to time because I'm taking the average value. I'm going to integrate over exactly one period. So I'm just going to choose to write that as 0 to t. I could just as easily write it from negative capital T over 2 to positive capital T over 2. Doesn't really matter what the bounds are as long as I'm integrating over exactly one period. Sorry for harping on this. Some of you guys learned this way back in pre-calculus. Well, I guess not pre-calculus because it's got integral in it, but you've dealt with it before, okay? So this is what we would get for a periodic signal, okay? Now, let's say that we have some non-periodic signal, okay? So let F2 of t be a non-periodic voltage signal. Once again, it's applied across a resistor RL. I'm not going to bother writing that bit down. And so how we would take the average value of this signal, we'd have to get a little bit creative, right? So our integration stuff is going to look effectively the same. So F2 quantity squared divided by RL with respect to time. So what would, and I know this is going to sound like a weird question, but what would the period of a aperiodic signal be? Infinitely long, right? So I'm still going to write this as from 0 to t, and I'm going to put 1 over t, but now I'm going to have to take the limit as I allow t to approach infinity. Okay. So in order for us to simplify our calculations, we are going to define, so let's a noise voltage as lowercase vn squared. And this will be the value of the average power divided by our load resistance. And this is going to come out to be the limit as period approaches infinity of the integral over one period of f2 of t squared dt. So for most physical noise sources, the instantaneous noise amplitude follows a Gaussian distribution. So let me write that down. So this means that roughly 68% of all noise amplitudes will fall between one standard deviation, or fall within, I think would be a better word to use there, sorry. Of the average noise value. And the probability of noise voltages exceeding 3 standard deviations. Sorry, that looks shitty.
On the noise folder.
I did. Thank you for that. Yes, absolutely. So the probability of noise voltages exceeding 3 standard deviations is less than 0.3%. So effectively, even though it's random, we have a pretty well-defined range of possible noise amplitudes that we might see, okay? The standard deviation yes.
This is probably a stupid question,
Nope.
but where you have your noise voltage defined, the Gn squared is equal to the average power over RL. Why is the average power over your load resistance? Like, I guess what I'm saying is average power is equal to V squared over R, right?
Mm-hmm.
So when you multiply them across, it would be
Quick aside here, let me start by saying that these notes are from 2009. So there's a very distinct possibility I just made an error way back when I was a grad student, but let's check things out. I see what you're saying. So P should be V squared over R. So you're saying that V squared should be equal to P times R. Now, what I think I'm trying to get here, and this is effectively saying that our noise voltage is independent of the size of the resistor that we're using, might be a better way to explain it. So kind of how we did RMS signals, which is actually what I'm about to get to. It doesn't really matter the value of the load resistor whatsoever. There's a proportionality between the power and the voltage. So let's leave it there, but I'll put a pin in it because there is a distinct possibility I am wrong. Yeah.
In the integration, RL is cancelled with the RL formula. If you see, in the integration, there is RL in the denominator and it's no RL. So RL is cancelled with that. That's why it's not mentioned.
What he said. I think it shouldn't be in there for what it's worth. Because the noise voltage squared, I mean, yeah. All right, so the standard deviation of the average noise voltage is known as the RMS voltage. And we're going to define that VRMS as simply the square root of our noise voltage. So this brings into question effectively whether or not noises are correlated or uncorrelated. Okay. So let me just make a quick note here. So noises can be correlated or uncorrelated. And let's talk about that really briefly. That's just a simple kind of thought experiment type thing. All right, so we are in this classroom and I am going to be an egotistical jerk as per usual. And I'm going to say that any noise, literally sound that I am making is intentional. And any sound that you guys are making is unintentional or noise, right? So all of you are individual students with your own individual idiosyncrasies, meaning you might shuffle your feet, you might shake a can and put it on a table, things like that. But you're just generating little bits of noise, and everybody's noise that they individually generate is independent of each other, okay? So that would be an example of uncorrelated noise, right? Now, let's put that in a different context. What if we were at a football game, right? And all of a sudden, the team that we are rooting for scored a goal. Well, then everybody's noise contribution is correlated because they are all reacting to the same event. So there is a fundamental difference between uncorrelated noise and correlated noise, just like there's a fundamental difference between correlated signals and uncorrelated signals, right? So if two noise sources produce uncorrelated noise voltages, VRMS1 and VRMS2, the total noise, VRMS total, will be the sum of the squares of the individual RMS noise voltages. for those of you who had me for earlier electrical engineering courses, this is literally the exact same equation that we use for finding like the RMS value of voltage signals that are operating at different frequencies. So if our excitation frequencies are uncorrelated to each other, meaning that we're just applying voltages directly, this is how we calculate those RMS signals, right? This is literally a circuits one relationship applied to something a little bit bigger. Now, if two noise sources produce correlated noise voltages, the total noise is simply VRMS total is equal to VRMS1 plus VRMS2. Okay, so let's shift gears very slightly. And now we're going to talk about noise in the frequency domain. So when I'm speaking, or Nathaniel or Jordan, and I'm sorry, I don't know more people's names are speaking, but when men are speaking, we generally produce a range of frequencies that is lower than when women are speaking, right? So noises can behave in a similar way, okay? And we can make these observations scientifically by looking at what's called the power spectral density of our noise signal, okay? So our power spectral density and I'm going to abbreviate this as PSD, is going to be given as, let's see, so let's see, is defined as the average power carried by a signal in a 1 hertz bandwidth around a specific frequency. Okay. So our symbol for this is going to be Vn squared with a bar over it. Okay. And our units are going to be volts squared per root hertz. Then our spectral density this is something that we're going to see every now and again. So this is just the square root of our power spectral density. Okay. So we'll give this a symbol of Vn without the squared with a bar over it. And it's going to be measured in, actually, that shouldn't have been root hertz. I got ahead of myself. My apologies. Volts per square root hertz. Sorry for that unit mistake there. Okay. So our RMS voltage will be given by VRMS is equal to the square root of the integral of our power spectral density as a function of frequency across all frequencies of interest. Okay. Let me just put a note here. Integration is carried out all frequencies of interest. There are two power spectral density distributions that we will see a whole heck of a lot, okay? And they are what are called white noise and 1/f noise. So white noise, goodness gracious, that looks horrifying. Is independent of frequency, which means the noise spectral density is constant. So if I looked at a power spectral density plot, where this is Vn squared as a function of frequency on the y-axis and frequency f in hertz on the x-axis, it would just look something like this. I'm going to kind of shade that in, right? So completely and utterly independent of frequency. Okay. Because real systems have finite bandwidth, measured noise will not be white, but will be shaped by the transfer function h of f of a system. So our measured noise would be given by something like this. So the noise power spectral density measured at the output of a particular system as a function of frequency would be the magnitude of our transfer function squared times our power spectral density. So effectively, if we had our white noise like this, and our system had a transfer function like this, where this will be the magnitude of h of f quantities squared. Let me just do this in blue. So a simple low pass response. Then our measured noise might look something like this. Right? So effectively, if we run noise that is independent of frequency through a low pass filter, we should be able to extract out all of the high frequency noise, which is the purpose of the filter to begin with, right? So nothing particularly wild or crazy there, okay? Our RMS value for white noise is going to be the square root of the integral of the absolute value, crap, so many brackets and stuff, I forgot something, of our transfer function squared times our power spectral density with respect to frequency. And we can pull out essentially our spectral density, and it'll be multiplied by the integral of the square of our transfer function's magnitude. Okay. And then our bandwidth will be 1 over the absolute value of the peak of the magnitude of the transfer function multiplied by the integral of the absolute value of the transfer function squared. The most common form of white noise is what we would consider thermal noise, which is just electrons moving around and all of that kind of stuff and generating noisy signals. Okay. At extremely high frequency, so on the order of tens of terahertz, so out of the normal usable electromagnetic spectrum for communication signals and all that kind of stuff, but before we get into visible light, so that intermediate region, our noise power tends to fall off. But for all principal electronics applications, we are going to consider electrical noise or thermal noise white noise, okay? So unless we have an extremely high bandwidth system, talking about above 100 gigahertz or more, we're going to consider thermal noise to be white noise. All right, so now let's talk about 1 over F noise, which I find more interesting. Okay. So 1 over F noise is inversely proportional to frequency, which is literally what the name means, right? So nothing real big there, okay? Generally speaking, it's caused by the random trapping and releasing of charge carriers in electrical components. So one of the most common places that we see 1 over F noise is in things like transistors. And let me explain why that is with a very shitty picture. Okay. So this is a oxide interface. Okay. So down below here, we have a very well-ordered crystalline structure, which I am shittily attempting to draw. Right? So we're talking about silicon. Our expectation is that we're going to have something like this, where all of our silicon atoms are covalently bonded to our 4 nearest silicon atoms. But when we hit an oxide interface, we've got a little bit of a problem because silicon dioxide is not crystalline in nature. It is an amorphous solid, right? So effectively, we're still going to have silicon atoms on this side, but they're not going to be nearly as evenly spaced. There's going to be oxygens also mixed in there. And so we're not going to have the same bonding that we might normally have. And so there are lots of free regions for electrons to just kind of get taken up and move around as those bonds just kind of shift into what lowest energy state we have available is. This is where 1/f noise comes from in most electrical components, is effectively dangling or unfilled silicon to silicon bonds that can randomly pick up an electron and then just release it out as another one comes by at a more favorable energy state. Okay. So we are going to define our 1/f noise, V 1/f with a bar over it. So this is our spectral density as a power spectral density multiplied by Fc over F, okay, where Fc is what's called the corner frequency. And this is where Vn squared has equal, amplitudes for both white and 1/f noise. So on a power spectral density graph, it might look something like this. So, and let's do this in log scale. So our 1/f noise is literally going to look something like that. So as our frequency increases, our noise gets lower and lower and lower. And then our white noise has a spectral density that looks something like this, where it is constant over all frequencies. So this guy right here represents 10 log of V1, sorry, that shouldn't be an I. This guy right here represents 10 log of our white noise. And then our corner frequency is this point right here, where the amplitudes of those power spectral densities are equal to each other. Okay. The RMS value of 1/f noise, 1/f noise, is going to be the square root of the integral from some low frequency to some high frequency of our white noise spectral density multiplied by corner frequency over frequency with respect to frequency. Or this will come out to be the square root of Vn squared times our corner frequency natural log of FH over FL. Okay, what time do we have? All right, we're still good. So let's talk very briefly about the equipartition theorem. And then we'll get into some specifics. Okay. So the equipartition theorem states that the average thermal energy for each degree of freedom in a system is given by W is equal to 1/2 kBT. A degree of freedom is defined as a component or direction, etc., that is capable of storing energy independently of other variables. So an ideal gas molecule would have 3 degrees of freedom because it can move in 3 directions, right? The X, Y, and Z direction. So it'll have some kinetic energy in those directions. They are independent of each other. So that's got 3 degrees of freedom. A harmonic resonator has 2 degrees of freedom. So we have the velocity of the proof mass. We can store energy in that way. And then we also have the position of the spring. So as we extend or compress the spring, there's stored energy. Okay. So now let's talk about, let's use this equipartition theorem and talk about thermal noise in electrical systems and then thermal noise in mechanical systems. So in an electrical system, the number of degrees of freedom is simply the number of independent inductors plus the number of independent capacitors. And what I mean by independent inductors is inductors that can't be simplified into an equivalent inductance. And independent capacitors, the same thing. I can't simplify them into a single equivalent capacitance. So they're connected in some way that I can't do component combination techniques. Okay. So for independent capacitors, our average thermal energy is going to be 1/2 kBT from the equipartition theorem, but we also know that a capacitor stores energy whenever there is a voltage across it, right? So we could say that this is going to be equal to 1/2 our capacitance C multiplied by the RMS voltage across it, and rearranging this, we get the RMS voltage or noise voltage across a capacitor is then simply the square root of kBT divided by the capacitor value itself. Yes.
Clarify, here K is the Boltzmann constant, right?
Yes. So I'm always going to use K subscript capital B to represent Boltzmann constant because we have spring constants that are also K, and I'm not intentionally trying to confuse anybody, although I'm sure I'm unintentionally doing it every time I open my mouth. But anyway, so that's what we get for our RMS voltage for a capacitor. And then for a current, we're going to wind up having some RMS current, right? So for independent inductances, holy crap, independent inductors, WL is going to be 1/2 kBT yet again because of the equipartition theorem. And hopefully we're all aware that the energy stored in a capacitor is 1/2 L times the current. So I'm going to put I RMS quantity squared here. And rearranging, we'll then find that our RMS current is just the square root of kBT over L. So resistors are not energy storage elements, but they will also have some noise associated with them, okay? Resistors are going to behave effectively as white noise generators, okay? So for a resistor, we are going to consider each resistor contributing a power spectral density of 4 times kBT times the resistance value. So the larger the resistance is, the more white noise it generates. Okay. So these are our noise contributions from an electrical system. In a mechanical system, goodness gracious, my handwriting is getting more atrocious by the moment. So the average total thermal energy, and that should probably be total average thermal energy, but I'm lazy. Is the sum of the kinetic energy stored in the mass and the potential energy stored in the spring. So if I have a simple system, this is a simple harmonic oscillator, or is what I'm trying to draw, where I have some, let me do it in blue here. So here's some proof mass M. Here's some spring with a spring constant K, no subscript on it because I don't know if it's a guided beam spring, a cantilever spring, or anything like that. So I'm just calling it K. And that will also help differentiate it from Boltzmann's constant K sub B. My spring is anchored on this side, and then I may also have some form of mechanical damping, which I'm trying to represent with this symbol, where the damping coefficient is going to be gamma. Okay. So this is the kind of system that I'm principally worried about because it most is simple harmonic oscillator is the most commonly used MEMS architecture. All of our gyroscopes, accelerometers, and things like that are literally just harmonic oscillators. Okay. So for our kinetic energy, we're going to have W kinetic is equal to 1/2 kBt from our equipartition theorem, right? If we allow our mass to move, it will have some amount of kinetic energy. And this is going to be equal to 1/2 times the mass times x RMS dot squared, where x RMS dot is the RMS velocity of the mass. So how much our mass, or the speed at which our mass is randomly vibrating due to thermal energy, effectively. So we could rearrange this expression to find that our RMS thermal velocity, or RMS noise velocity, is going to be the square root of kBt over our mass. And then for our potential energy, and goodness gracious, we're going to have W potential. Once again, 1/2 kBt from the equipartition theorem, and the potential energy stored in a spring is given by 1/2 times our spring constant K times our displacement. So no dot on this one. Rearranging then, we have x RMS is equal to the square root of kBt over K. So just to be real clear here, numerator Boltzmann constant, denominator spring constant. And then lastly, to account for our mechanical damping, this is the equivalent of resistance in an electrical system, right? So we are going to generate a noise force spectral density that will be equal to 4 kBt times gamma. All right. So the last couple of things that I want to talk about here really quickly are what are called input referred noise and signal to noise ratio. So we are going to refer any noise in our systems to the input of the system particularly, so that we can effectively compare our input referred noise to the size of our signal to see whether or not we can actually measure anything at the output of our systems, okay? So input referred noise allows for an instantaneous comparison to our signal level, right? So if we had a simple amplifier, right, where this amplifier has a gain of 100, our input signal on this side will be V sig, and let's call that 10 microvolts. Our output signal, the out, is just going to be our gain times our input signal. So this is just going to be A V sig. So 100 times 10 microvolts would be 1,000 microvolts or 1 millivolt, right? Now, we are very rarely going to be dealing with pure signals. So instead, we might have something like this, where we've got our input signal V sig and some input referred noise voltage, like so. VRMS in will be combined together, fed through our amplifier A, and give us our output signal VRMS out. Now, typically speaking, we're not going to be able to measure the input referred noise voltage. We're going to measure the voltage, the noise at the output of our signal. So our input referred noise voltage, is literally just our output referred noise divided by our amplifier's gain in this case. Now, I don't want to get too far ahead of myself here, but we're talking about this as if it were in terms of simple voltage signals right now, and there's nothing particularly wrong with that, but we're going to actually wind up using these kind of signal flow diagrams for literally everything. So like if we want to convert a displacement into a force, we might consider our spring an amplification stage and stuff like that. So we'll break things down fundamentally in smaller digestible pieces, and then we'll put the noise in where they are appropriate, and then refer everything back to the input to get a total picture of what's going on, what type of signal levels we should be able to measure from a system. So it'll be a little bit more clear once we start talking about a specific device as opposed to signal in, signal out, ratio, that kind of thing. All right. So if we had multi-stage amplifiers, so let's say that I have some amplifier here, A1, some amplifier here, A2, like so. And then this is where we measure our RMS output noise voltage. Then our RMS input noise voltage, VRMS in, is going to be the square root of, let me put another signal right here. So this will be VRMS out 1. Okay. So VRMS out 1 quantity squared over A1 squared plus VRMS out for the system squared divided by A1 squared times A2 squared, where we are making an assumption here that our amplifiers are effectively creating uncorrelated noise. Okay. So from this relationship, we can actually see that the order in which we place our amplification stages can play a critical role as to what our input referred noise might be. Okay, and I think I've got a homework assignment for you guys to play around with that. The last little mini thing that I want to talk about, and this is going to be ridiculously quick, is signal to noise ratio, or SNR. So signal to noise ratio, symbol SNR, is literally the ratio of the power of the signal that we're interested in divided by the power of the noise, which would be then the same thing as the square of the RMS value of the signal divided by the square of the RMS value of the noise. Typically speaking, this is actually something that's measured in decibels. So we can define SNR in decibels to be 10 log base 10, the ratio of the powers, which will be the same thing as 20 log base 10, the ratio of the voltage signals. And these voltage signals for noise and signal should not be squared here because that's what the 20 is taken care of out the front. Okay. So a signal to noise ratio is a way for us to very easily characterize signal quantity, signal quality. And this is usually something that's going to be defined by the application or something like that we're trying to do, right? So if let's talk about Allie's line of study really quickly, a biomedical engineer, and we are trying to measure brain waves or something like that. Those signals are going to be incredibly small. So if we had a signal to noise ratio of less than probably 3 or 4, the information that we're interested in is going to be largely buried, right? If we had a signal to noise ratio of less than 1, meaning our noise power is greater than our signal power, we can never pick up what it is that we're actually trying to find. So that's why SNR is commonly used to make comparisons. All right, that's enough out of me for today. See you guys on Monday.